Hello, I'm Octavio Perez, and I earned a Ph.D. in multidisciplinary science at Rensselaer Polytechnic Institute and at doing the research at Mount Sinai Hospital. And I'm working now as an international consultant and investigator at Mount Sinai Hospital in the field of human-centric lighting. We are going to discuss today the very basics of human-centric lighting. Particularly why spectral power distribution is so important rather than color perception, including illuminance. We know that light and lighting affect human health and well-being in the built environment beyond the visual function V lambda, and this will take us to human-centric lighting. Lighting illuminance is typically measured in lux, and the lux is the weighted visible flux of the total radiant flux per square meter in the visible region of the electromagnetic spectrum going from 380 to 780 nanometers. So with this, the question is if we can properly measure the non-visual illuminance of light and lighting through the visible illuminance measured in lux. To cover this, we will go through, in this presentation, through these points. First, we will give a definition of what is integrative lighting, the basics of human-centric lighting. Then we will go into briefly discuss the metrics, melanopic equivalent daylight illuminance versus the lux. Then we will go into what is really needed, that are human-centric lighting performance metrics and how to evaluate them. And in this presentation, we will cover the first point, that is spectral power distribution and melanopic versus color perception in CCT and CRI. And in other presentations, we will cover vertical melanopic illuminance versus horizontal illuminance, and we will also do energy considerations in human-centric lighting. Then we will discuss a couple of metric limitations, basically directionality and age, but not only these ones. And then we will go into the conclusions and lessons learned. So going into definitions, because it's quite important to define what we are speaking about, we have at least three that are valid today. The first one is from SWEI, from the German Association of Electronic and Electric Manufacturers. And it's in German, but basically it is looking at the effect of visual, emotional, and biological effects of light in people. If we go into the CIE, there is a definition that is being upgraded, and it basically says that it's lighting, not only light, but lighting specifically designed to produce a beneficial physiological and or psychological effect upon humans. So we are speaking about psychophysiological effects. And this includes both visual and non-visual effects. And finally, we have another one from Lighting Europe and IILD, that is human-centric lighting supports health, well-being, and performance of humans by combining visual, biological, and emotional benefits of light. But again, it's lighting, it's not only light. Going into a visual concept of what is human-centric lighting or integrative lighting, first we have to consider the visual ergonomics and the environment, and we have a couple of regulations here that have been in place for a few years already. Daylight was introduced a couple of years ago. Then we have the health, where we can think in terms of well and fit well. And then we have the energy, that is in standards such as LEED and BREEAM. So human-centric lighting or integrative lighting can be understood as the intersection of these three: visual, health, and energy. Now that we know what we are speaking about, and without going into deep details, we have basically two weighting functions that are going to help us evaluate this field. One is V lambda, the visual function. And then we have the melanopic function, that is the whole light is affecting the IPRGCs that are the main sensors, not the only one, but the main sensors to evaluate effects of light and lighting in humans. The first metric that was used was called EML, and it is discussed in the well building standard and used in version 1 and version 2.1. I'm not going through the details, but it's basically a relationship between the photopic illuminance and a ratio that takes us to the vertical, I mean, in this case vertical, but it's to the melanopic. We can either go through a table that is discouraged, and we should go into spectrum evaluation. So we have to get the SPD of the lamp or the fixture, but at the end is the environment. And then we have a weighting factor that will take us from, and function that will take us from melanopic, from photopic into melanopic. But this is not the one that we should use anymore. The CII has proposed a melanopic equivalent daylight illuminance. And basically it's the photopic illuminance unit lux, that is according to the International System of Units, produced by radiation conforming to standard daylight, D65, that provides an equal melanopic irradiance as the test source. What this means is that, as we said, the melanopic equivalent daylight illuminance, and here we have the stimulus of the lighting conditions. And if this is the SPD for D65, here we get the visual illuminance that D65 is giving for this melanopic illuminance. And this is what we are going to do to evaluate this melanopic. What we will do is to estimate, to calculate this one and go to D65 and check which is the visual illuminance that we are getting. These are the relationships between melanopic equivalent daylight illuminance and EML. Here we have one. And here we have it from as a direct product of the melanopic irradiance. This has not been officially published, so it's a good idea to have these references. Today, we already have equipment that will give us these calculations directly, like this one from High Gigahertz Optic, a Sensatec, or GL Optic. But it's also a good idea that we calculate this on our own if we want to know what's going on behind the calculations. And this is what we are going to do here. So we will do calculations of melanopic equivalent daylight illuminance for different light sources of different CCT and CRI commercial LEDs and see what is happening. As I said, CCT is not the right metric for melanopic and for SPD, but in commercial, it will give us an idea. So what we will do is we will get the SPD in steps of 1 or 5 nanometers of different light sources. In this case, we are working with sunlight from Seoul Semiconductor, full spectrum. We will do a normalization, maximum 1 value, and then we will do 2 calculations. We will go into equal photopic in 100 lux, and we will calculate the melanopic contribution in melanopic equivalent daylight illuminance lux. And then we will do the opposite. We will having equal melanopic in 250, we will estimate which is the photopic requirement in lux to achieve this melanopic illuminance. And in another presentation, we will cover the real environment in the performance metric, horizontal versus vertical, because the idea is to have the photopic in the horizontal and the melanopic in the vertical and calculate the ratios between both. So if we go here, as we have discussed, we have V lambda for the visual, and we have the melanopic for the non-visual. And going into full spectrum LEDs, this is what we get if we plot the SPDs. And we can see that for an equal photopic condition, this is what we get for 2,700, 3,000, 4,000, 5,000, 6,500, and daylight. So if we plot one by one, this is what happens with 2,700, 3,000, 4,000, 5,000, 6,500, and daylight. So this is the plotting of the SPDs of these light sources for an equal photopic condition. The question is, what's happening in the non-visual? And this is what we need to evaluate. So if we go into the detail of the non-visual, this is what we get. Let's go step by step. So this is the visual, and for all the light sources, we calculate the photopic that is going to be this one. And for this equal photopic condition, this is what we get in melanopic. This is what 2,700 is providing, 3,000 is increasing the melanopic, 4,000, 5,000, 6,500, and daylight. So we can see that as we increase CCT, we get more melanopic stimulus for the same visual stimulus. So let's go into the details. In this equal photopic condition of 100 lux, let's calculate what is the melanopic contribution for the different light sources. And this is what we are working with. We are going to work with different CCTs in commercial LEDs and with different CRIs and D65, and we will see what happens. And if we plot, this is what we get. And again, let's go step by step. So if we go into 2,700, we see that for CRI 80, we get a melanopic of 3994. We increase with 90, we increase with CRI 95, and with the full spectrum, we go to 4587. This is what happens with 3,000, and we can see something similar. In 4,000, this increase is even bigger, higher. We see an increase in around, or even more than 20%, going from 59.30 to 71.94. 5,000, same, and in 6,500, we see that with a CRI 90 LED, we are around 90 melanopic lux, and in full spectrum, we are almost the same. We have 100 photopic and 100 melanopic. So this means that with 100 photopic lux, we get 99.95 melanopic equivalent daylight illuminance lux against 39.94 that we get with a CRI 80 at 2,700. Let's see the picture the other way around. So if we want to have this melanopic equivalent daylight illuminance in 250 lux, how many lux do we require from Photopic. And this is what we get. Same family of LADs here, and CCTs and LADs, and these are the values. Let's plot them. And here is the total plot, and let's go into details. If we go into 2,700, we see that to get 250 looks with a CRI 80, we need 625.9 photopic looks and 545 in the case of the full spectrum. This requirement lowers as we increase the CCT. And going down to 6,500, we see the same as before, that to get 250 melanopic equivalent daylight illuminance looks, we only need 250 photopic looks. So what we have here is that to get 250 melanopic equivalent daylight illuminance looks, we require 625 looks with CRI 80 at CCT 2700, but we only require 250 looks with full spectrum 6500 Kelvin. So as a summary, and this is why SPD is so important, as we increase CCT and CRI, we can expect more melanopic stimulus on an equal photopic condition and less photopic requirement to achieve a certain melanopic stimulus. But SPD is only half of the story. What is next? This we will see. This is quite important, this slide. What this slide is showing is that you can be confused depending on how you see the plots of the SPD. So this is all the sources that we have been working with are plotted here in a normalized way with a maximum 1. If we move into 100 looks, this is what you get. And if we move into equal melanopic at 250, this is what you get. So you have to be extremely careful in the way you evaluate the plots of the SPDs, not to be confused with the relative versus the target. So going into the metrics limitations, the main one are field of view and directionality still is a very important one that is described in the CIE documents. And basically what it says is that the angle of incidence of light in the retina, that is here at the bottom side of the retina, what this means is that the light that has more effect for melanopic is the one that goes from 0 to around 45 degrees. As we increase, we have a little less effect, and here can be even disturbing. And this is the light, the one that comes from the bottom and that goes to the upper side of the retina is the one that you have to be very careful with, because you can create a lot of glare, as we or I did not evolve to have to get light here. We have evolved to get light here from the sky. The other limitation that we have is age, and this is also described in the CIE document. And we have to do this evaluation according to the average vision for age of people. And what happens is that as we age, our lens becomes more yellowish up to a point that we don't see. And this is when we have to go into surgery. And here you have the graph that plots how we lose spectral perception, basically from, let's say, around 500, 550 downwards. So, which are the lessons learned in this presentation? That we need new metrics for human-centric lighting, integrative lighting. The main one is the melanopic equivalent daylight illuminance, D65, that has been proposed in the document CIE S026 2018. And it is International System of Units compliant. No other one is. These visual and non-visual metrics have limitations. So it's not only about the visual, the non-visual. The visual also have limitations. First of all, you have to be careful with the SPD graphs, and we will insist on this. Directionality is important, the angle where the light enters into the retina, and the age. And there are more limitations, but these are the basic ones. And the most important thing here is that the non-visual illuminance metric is only the first human-centric lighting, integrative lighting dimension. This is the starting point. So finally, I would like to insist in this, be very careful with the way that you evaluate SPDs so that you are not confused between relative or normalized and target SPDs. And this is it for now. So thank you very much for your attention. And I hope that you have enjoyed the presentation and that we will provide more materials in the future. Thank you.